Welcome back to part 6, our final part of disconnecting means, where we're going to talk about accessibility and we'll look at a quick design example. 404.8a of the National Electrical Code says any disconnecting means, either a switch or a circuit breaker, can have a maximum height that's from where the center of the handle is of 6 feet 7 inches. We can see in this photo that that disconnect is relatively high on the wall. The top of that handle cannot exceed 6 foot 7 inches. So when we're planning our installation and how that's going to go, we need to make sure that we are going to meet those requirements. When we have an EPC, which is an electronic power converter, that would be inverters, microinverters, DC to DC optimizers, charge controllers, we can put those in what is considered a not readily accessible location. So in the slide we can see a roof installation where there are microinverters or DC to DC converters being installed on the roof attached to the racking, which will be underneath the array. That is allowed. However, they must have an equipment disconnecting means per Article 690.15, which we talked about in the last section. In this case, with these microinverters, both the DC quick connectors that connect to the individual modules and that AC connector that attaches to the trunk cable have been listed as load break rated disconnecting means. So that would be our equipment disconnecting means for this installation. In most cases, if you're servicing a microinverter, you're going to shut off the circuit breaker at the AC branch circuit for that microinverter, which is a load break rated disconnect, and that will de-energize that circuit so there's no current flowing through the circuit. Of course, we're going to test the circuit with our clamp on amp meter before we disconnect anything and make sure there's no current flowing through there, and then we can disconnect those module quick connectors and the trunk cable quick connector, although they are load break rated in most cases with AC microinverters. We need to ensure that that is the case if we are going to use them as load break rated disconnects. But again, most of the time we're going to shut the circuit breaker off, we're going to lock it out, and then we will be able to disconnect those equipment disconnecting means on either side of that microinverter so that we can service or replace it as necessary. Again, read your free manual, RTFM, and make sure you know how those connectors on those electronic power converters are listed and how they need to be used. Let's talk about an example of sizing our disconnects for a DC combiner. In this system, we have 24 source circuits in each combiner. Each PV source circuit is rated at 8.72 amps, and we are going to use 2 source circuits per fuse. It's a little bit unusual, but it allows us to use less fuses, which reduces our balance of system cost. We have 29 modules in series for a maximum system voltage of 1,426 volts DC. That's under the 1,500 volt limit for our equipment. We know from looking back at our previous lessons that this must be a large scale system that is not on a building to have a voltage above 1,000 volts. When we size our combiner, we take the 24 source circuits, multiply that by 8.72 amps per source circuit. We're going to multiply that by 1.25 for the fact that our PV source circuits can operate at a current level above standard test conditions if our irradiance is above 1,000 watts per meter square. That gives us 262 amps. Obviously, we can't get a 262 amp fuse, so we're going to round that up to the next standard size, which is 300 amps. Now, if that fuse is rated for continuous current, we're okay, we can use that 300 amp fuse, but it has to be rated for continuous current or full rated duty. If it is not rated for continuous current, we would need to multiply that 262 by a second 1.25. That's that continuous current rating requirement of the National Electric Code, and we would have to round up for 350 amps. So that would be your standard fuse size, a fuse that is not rated for continuous duty. This combiner box has an integrated disconnect. We can see it here on the picture. That's what this device is in here. So we have our PV positives coming into our fuse holders, into this bus bar, into the disconnect. We have our negatives coming in here to a common bus bar connected in parallel there and through this disconnect. So this disconnecting means is disconnecting both the positive side and the negative side through this switch here. And then our output circuits come and connect to these terminal blocks here and go out to either our recombiner or to the inverter. We have 12 fuse holders in this combiner box. Each fuse holder is connected to 2 PV source circuits, which are connected in parallel using a Y connector out in the field. This combiner box is rated to UL 1741 and has a voltage rating of 1500 volts DC to match the maximum circuit voltage of our system. We need to verify that the terminals of this combiner box are large enough to accept the conductors that we are going to be working with. We need to size our conductors both for the ampacity that the system is going to be working with and for voltage drop, decide what size that conductor will be, and make sure that the terminals on the combiner box are large enough to accept that size conductor. Here we see the PV output circuit. They're actually using 2 conductors in parallel for both the positive and the negative, so they can use a smaller conductor and connect to those 2 terminals here. In this case, you'd need to make sure that the combiner box had 2 terminals on each of those positive and negative output circuits. That is the end of our lesson on disconnecting means. I hope that you learned something useful. If you have any questions, please feel free to post those in the forum and your instructor will be able to answer those. Thank you for joining us and have a great day.